Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Potential Energy, Gravitational and Elastic. As always, please be an active learner as you watch these videos. An object gains or loses kinetic energy because it interacts with other objects that exert forces on it. We've learned that during interaction, the change of a particle's kinetic energy is equal to the total work done on the particle by the forces that act on it during the interaction. But there are many situations in which it seems as though energy has been stored in a system to be covered later. It's like a savings account in a bank. You deposit money and then you can draw it out later. When we raise the hammerhead of a hammer into the air, we're storing energy in the system, energy that is later converted into kinetic energy as the hammer is released and falls down. Or consider a pogo stick, in which the spring is compressed as you jump on it and then rebounds, launching you into the air. Or a mousetrap, in which the spring stores energy that is released when the trigger is tripped, and so on. All of these examples point to the idea of an energy associated with the position of bodies in a system. In some cases, changes in this energy may accompany opposite changes in the kinetic energy in such a way that the total energy remains constant. Energy associated with position, such as this, is called potential energy. Forces that can be associated with potential energy are called conservative forces. A system in which the total mechanical energy, both kinetic and potential, is constant is called a conservative system. As we will see, there is potential energy associated with an object's weight and its height above the ground. There's also potential energy associated with elastic deformation of an object, such as stretching or compressing a spring. Let's talk about gravitational potential energy first. So if I have a box that's at rest at this height and I let it go, it will start falling and start moving faster and faster and faster due to the acceleration of gravity. The force here is the mass times the acceleration due to gravity, and it will be going faster and faster because it is accelerating. So what you have is that the difference between the final y-coordinate and the initial y-coordinate. The initial y-coordinate is up here, the final y-coordinate is down here, is less than 0. So the gravitational potential energy decreases. And what's really happening is there is an element of gravitational potential energy here that's being changed into kinetic energy here. Or we can take something and we can be initially at this height, but we can lift it up and have it prepared to be dropped later. So in this case, y sub f minus y sub I is greater than 0. So gravitational potential energy increases. And so the change in gravitational potential energy is greater than 0. For some reason, in many books, they use a U for this potential energy. All that thinking leads us to define gravitational potential energy here. When an object with mass m is a vertical distance y above the origin of coordinates, the gravitational potential energy U sub grav, G-R-A-V, that's potential energy, gravitational is what that notation means, of the system is U sub grav is equal to mg times y, where g is the acceleration due to gravity. Now, if you think about this, the units of this are going to be joules. And here are some notes about this equation, and the equation should be committed to memory, or at least you know where it is on the grace notes, so you can always use it. So the notes. This expression for gravitational potential energy is valid only near the surface of the Earth. Almost all of our problems will be near the surface of the Earth unless specified otherwise. U grav is a scalar quantity, just like work, which is energy. It can be positive, negative, or zero. Finally, in problems where the only potential energy is gravitational, we'll sometimes omit the grav subscript entirely and simplify the notation just to call it U. And so the way to think about the mechanical energy then, kinetic plus potential, in this gravitational system is going to be, if this is the E, then E is equal to the sum of kinetic and potential. And that is the initial energy. And the energy at the end is going to be the sum again of the kinetic and the potential. Whenever the vector sum is zero, the total mechanical energy is constant or conserved. And so this is a property that we will often use to solve problems. You see, the kinetic energy at time 1 plus potential energy at time 1 is equal to the kinetic energy at time 2 plus the potential energy at time 2. Energy is conserved. Okay, let's do this to work a problem that will be similar to the kinds that you would be asked to do on an assessment perhaps. And this is the height of a baseball, and we'll do this using energy conservation. So here we use the conservation of energy to tackle a simple free fall problem. You throw a 0.150 kilogram baseball straight into the air, giving it an initial upward velocity of magnitude 20 meters per second. Use the conservation of energy to find out how high it goes, ignoring air resistance. You know what to do. Let's see how you did. So we're going to use that kinetic energy before equals kinetic energy after. So this is 1/2 m v sub initial squared plus mg y initial, and that's equal to 1/2 mv squared final, and this is going to be mg, and then as y final. So you see, this is the conservation of energy that we're using. Now we're going to plug in numbers into this this equation, and in fact the only thing we don't know, we're taking this initial position to be 0, our initial point, and so that is 0. So the only thing that we don't know is we don't know this final point, y sub final. So what we're going to do is we'll make the equation, but that is going to be y sub final. And so you see, we have this y sub final. We plug in all the numbers. This is what we get on the left-hand side, and it's equal to this on the right-hand side, and there is where your variable y sub final is. So we use algebra, plug in those numbers, and we find that y final is 20.4 meters. We now turn our attention to elastic potential energy. And in elastic potential energy, we're going to be talking about the spring model. And this, as we talked about last time, obeys Hooke's law. That is, the force in either stretching or compressing a spring, a distance of x, is F, is equal to K times X, where K is the spring constant. So the associated potential energy, and here's an example of stretching or compressing. If we are at equilibrium, nothing's happening. If we pull it this way, it's force to do this, but the spring is also pulling us back with a force. Similarly, what can happen here is if you compress a spring, then the spring is tending to push you in the opposite direction of your compression force. So anyway, when a spring that obeys Hooke's law, F equals Kx, is stretched or compressed a distance x from the undistorted or equilibrium state, the associated potential energy, U sub L, is given by U sub L is equal to 1/2 K, and then this is x squared. The units are going to be joules, and these are notes. Again, it's a scalar quantity, and it's always positive. X is the amount the spring is stretched or compressed relative to its undistorted length. As a little bit of an aside, but a real-world application, one of the world's most famous climbing rocks is the El Capitan summit in Yosemite National Park. A common climbing route involves an overnight stay on a ledge. This is only for serious climbers. For a typical 75 kilogram male climber, the change in gravitational potential energy from the bottom to the top is, well, you just have 884 more meters of height, is about 6.5 times 10 to the 5th joules. Now that sounds like a lot, but in fact it's less than the energy you get from eating a typical candy bar. So the work that results is the net change in gravitational energy is only a small part of the total energy expended on such a climb, because what happens is you're not really just going straight up like that. What you're doing is you're going sideways, and you're in fact many times lifting your body in various directions to get to the top. Now, the work energy theorem says that the total work is equal to the change in the potential energy of the work associated with the elevation, and the work energy theorem, moreover, tells us that the kinetic energy plus the, let's say, the initial kinetic energy plus the initial elastic potential energy is the same, because it's conserved, as the initial potential, as the final kinetic energy plus the final position energy. So in this case, again, energy is conserved. Let's do a problem to make these concepts real for us. And we're going to talk about potential energy on an air track. So what we're going to do is we're going to have a glider with mass m equal 0.200 kilograms sits on a frictionless horizontal air track connected to a spring of negligible mass with a force constant of, this is the K for the spring, is 5.0 newtons per meter. You pull on the glider, stretching the spring 0.100 meters, and then you release it with no initial velocity. The glider begins to move back toward the equilibrium position, which we're calling x equals 0 here. What is the speed when the position is x equal 0.0800 meters? You know what to do. Let's see how you did. Okay, so here are some facts, okay, associated with the statement of the problem. So we're taking x equal to 0 to be the equilibrium position. So that's where we have in the picture. And the initial and final positions are, the initial position is going to be here at 0, but then we stretch it out like this. So x final is going to be, so x initial is, oh actually x initial is not, x initial is 0.100. Okay, so that's the initial position. But then what we're doing is we're getting a final position, which x final is going to be equal to 0.08 meters. Okay, so you see we've extended this much, and then we're going to let go of it. And then what happens is our final position is going to be, when we let go, it's going to be pulling backwards. When it gets to this position, which is a small number that is smaller than this, we're going to say what is its speed at that point in time. So this is initial, this is final, and the spring constant is 5.0 newtons per meter. Okay, so we can think about the kinetic energy then. So the kinetic energy at the initial point was zero. It's not moving. It's at rest. The velocity is zero. But at the initial position, there is potential energy, and you see it's going to be 1/2 k, and then this is 0.1 meters, but that is whole squared. If you do that calculation, you get this. So that's how many joules we had. Then the final kinetic energy we want to find, this is 1/2 m, and this is V final squared. So you see the spring is pulling it back towards the equilibrium. So the final this one is going to be, this is not at 1 anymore, this is at 0.08 meters whole squared. So you see some of this potential energy has been changed into kinetic energy, and the only thing we have to solve is this. So let's set up our equation. So the kinetic energy before plus the potential energy is the same as kinetic energy after, plus the potential energy after. So I substitute those values in. The only unknown is this V sub final here squared. So I solve this for V sub final and take the square root. Now, one should note that in this problem, the energy method is much easier to solve than the earlier method. In fact, it's very difficult to solve this problem with the earlier method. But the energy method, in contrast, offers a simple and elegant solution. Let's do another problem. A block initially traveling at a speed v falls onto a spring that is at its relaxed level. So the spring's just sitting here, and this is the initial v that it hit. The block remains in contact with the spring and continues to fall until it comes to a stop eventually down here. And what you can see is that it came to stop after compressing the spring by a distance of d. So the spring went from there to there, and that's compressing it by d. But now all this potential, all this kinetic energy, 1/2 mv squared, has been turned into potential energy with the spring, sort of like the pogo stick. So anyway, the question is, which statement correctly describes the change of the kinetic energy of the block? The gravitational potential energy of the block and the elastic potential energy of the spring as the block comes to rest. So there are two questions that you're answering, and there's two answers. And so what you have is a discussion both of gravitational potential energy, spring potential energy, and kinetic energy, all three. You know what to do. Let's see how you did. So here's the picture over here. So let's think about the changes in the kinetic energy of the block. Because the block was initially moving and comes to a stop, the kinetic energy must decrease, because the kinetic energy depends on speed, not the velocity. So the direction of the motion has no effect on kinetic energy. Now let's consider the change in the potential energies. In this problem, we have a block that is changing heights and a spring that's being compressed. Therefore, we have two potential energies that are changing as the block comes to a stop. The gravitational potential energy depends on its height. As the block falls, its height increases. So this potential energy of gravitation must decrease as well. As for the elastic potential energy, we need to pay attention to whether the spring is being increasingly stretched or compressed, and EL will increase, or whether the ball is returning to its relaxed position, and EL will decrease. Because the spring was initially at its relaxed length and becomes more compressed as the block falls, UL must increase as the block comes to a stop. Therefore, if you look at all the possibilities, A is the correct answer. In closing, Now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.